so in the last time, we was solving this equation. dt of u is dxx of u. Alright? And the equation is solved on axis from 0 to 1. And t is from 0 to infinity. Alright? So we have boundary condition at 0. So at x is equal to 0, this is equal to 0, and x is equal to 1, this is equal to 0 as well. When t is equal to 0, uxt 0 will be x, right? So this is the heat equation that we were trying to solve in the previous class. So you have the first derivative in t is equal to the second derivative in x. You have three boundary conditions, all right? Two boundary conditions and one initial condition. And x is equal to 0, ux at 0, t 0, and x is equal to 1, u1 t is 0, and when t is 0, you have the initial condition to be x, all right? So what you do is step number 1, you do splitting, right? uxt is tt times vx. So in order to solve this equation, you use separable method. First, you define u to be t times v. T is a function of t, and v is a function of x, right? So then you found two equations. dt t prime of t plus lambda tt is 0. V second of x plus lambda vx is 0. For the second equation, you have also a boundary condition. You have vx at 0 is v1 is 0. All right? So basically, the boundary condition of the second equation is coming from the boundary condition of the initial PDEs. All right? Explain again. To solve the heat equation, the first thing you have to do is to use a separable method. You suppose that the solution is a product of a function of t and a function of x. You replace all of these and that into the equation, you will find that t prime plus lambda t is 0 and v second plus lambda v is 0. The two boundary conditions for x will be the two boundary conditions for v. Right? So this system is separable because you have one equation for t and one equation for x only. Right? So step number 2, you solve the second equation. You solve the second equation and you find lambda n will be. So in the previous class we found lambda n is n minus 1/2 pi squared. N minus 1/2 pi squared. Alright? And all of the eigenfunction will be cosinus, Vn will be cosinus of n minus 1/2 pi x. Alright, so to solve the second equation, this is very standard. This is an eigenvalue problem, and after you solve it, you found lambda and Vn. Right? So step number 3, you plug lambda back into the equation, right? So you have Tn prime plus, so solve number 1, lambda nt is 0, and this gives you lambda nt is exponential, not lambda nt, this is Tn. So Tnt will be e to the power minus lambda nt. Alright? So after you found the eigenvalues in the first in the second step, you replace it into the first equation, right? So step number 1. All right, you replace it into the first equation, and you find Tn will be exponential of minus lambda nt, right? So step number 4, you put everything together, you will get that utx will be the sum when n is going from 1 to infinity. Cn e to the lambda n t cosinus of n minus 1/2 lambda x. So this is the basis for the x space, and this is the basis for x and t space. All right, it's clear. So I explain again. To solve a PD, what you do is you solve 2 ODEs only. How do you do that? You use a separable idea. You suppose that the solution is a product of a function of t and a function of x. You plug this into the equation, then you have 2 different equations. The first one is a first order differential equation of t, and the second one is a second order differential equation of v. So the boundary condition will be the same for the second equation. The boundary condition will be the same with the boundary condition of the heat equation, right? So you have ux, this is going from here and this is going from here, right? So the ux will be vx, u1 will be v1, right? So after you solve the eigenvalue problems, you will find lambda n to be of this form, and Vn will be of this form. You plug lambda n back into the first equation, you find Tn is exponential minus lambda nt, right? So when you solve the eigenvalue problems on x, you will have a basis for the x space, right? But now you have the t and x, so you multiply both of them and you have a basis for both of them, right? So now the key is to find this Cn, but this Cn is easy, right? So to find Cn, you will replace 0. You will use the initial condition, right? So you replace t to be 0 into the initial condition, all right? And you will find the sum when n is going from 1 to infinity of Cn e to power minus lambda n 0 cosinus of n minus 1/2 pi, right? Pi x, right? So this is going away. So x will be the sum when n is going from 1 to infinity of Cn cosinus of n minus 1/2 pi x. So x Cn, right? So now you use the initial condition. You replace t to be 0. When you replace t to be 0, this guy goes away because exponential of 0 is 1. All right? So Cn will become the coefficient of x in this expansion. All right? So how do you compute Cn? Cn will be integral from 0 to 1 of x times cosinus of n minus 1/2 pi x dx over this guy pi x squared dx. So the first term was computed in the previous class. The second one can be computed easily. It's 1/2. So this guy is 1/2, right? So in order to compute this, you can go back to one of the lectures in which we computed this guy explicitly. So the final answer is the following. Sinus of n minus 1/2 pi over n minus 1/2 pi minus 1 over n minus 1/2 pi squared. And then you divide everything by 1/2. So you multiply by 2. Right? So this is the final answer. Questions? Right, so in the previous class, I computed for you this guy, but this guy can be computed very easy. Right, so you have cosinus square is 1 plus cosinus of 2x over 2, and you do it, and you see this computation, this result, right? You want me to compute that?
No.
All right. So I explain again. So to compute that, it is simple, right? So you have cosinus of n minus 1/2 pi x squared will be 1 plus cosinus of 2 times n minus 1/2 pi x over 2. You replace this into the system. This one is going to be 0, so the level over is 1/2. Right? So I explain again. So this is the general method, the general strategy for you to solve a heat equation, and for the wave equation as well. This is the so-called separable method that we, in one of the tutor videos, I explained to you how to use separable method to solve first order differential equation. But separable method can also be used to solve PDEs, and this is one of the most powerful method. All right. Now, how do you use separable method? You suppose that U is a product of a function of t and a function of x. All right. You plug this into the equation. Then you find two equations. One equation for t and one equation is for x. So the power of this method is that you have you split x and t into two equations, right? So you split x and t into two separate equations. Right? So this is the power of this method. When you use this and that into the equation, you split x and t into two different equations. The first equation is the first order differential equation in t, and the second one is the second order differential equation in x, right? Now, you solve the second equation. So the boundary condition of the second equation will be the same with the boundary condition of the heat equation. So to solve the second equation, you follow the standard eigenvalue problem, and you find lambda is of this form and Vn is of this form. You plug lambda n back into the equation. So you have the solution for the equation for t, the first equation. So now you have two solutions. The first one is this guy, and the second one is this guy, right? So you multiply. So this is the basis for x space. You multiply them and you find a basis for both x and t space. So when you sum all of them, you need to find a coefficient because you want to expand it on a basis. So the coefficient can be computed easily by using the initial condition. You replace t to be 0, so the exponential will go away. So the initial condition will be Cn times the basis, right? So Cn will be the coefficient when you expand x on this basis. So you compute Cn by using the classical formula, right? And this will be the focus of the exam. Questions? It's clear? Yes?
How did you know the basis is still orthogonal when we did the product?
They are orthogonal because they are separate, right? So when you multiply two vectors, you integrate in x and you integrate in t, right? So when you integrate in x, it's already 0.
Okay.
Right? So of course, if this is not altered choice, you have to add a weight. But because, right? So when you multiply in t and you integrate in x, right? E to the power minus lambda n t phi n x. Phi n is this guy, Vn, sorry. Right? So this and this, when you integrate, is going to be 0. So it's, in general, they are orthogonal. So for the heat equation, so this form of basis, but this guy is not the true function, the true weight. So if you go to weight equation, you will see that you have to integrate this to see that this is 0, right? So the weight equation is more difficult. So for the heat is exponential, it's very easy, right? Other questions? So I posted two I posted two, yes. So I posted the practice exam online, right? So we're gonna go through the practice exam today for this week, and next week we're gonna go through the wave equation. So the wave equation will be in the exam as the optional questions, right? So the exam will be 25, right? I think so. So 12.5 will be, each problem will have 12.5. So the optional will be 12.5, right? Questions? So the exam will have two questions on the heat equation, and those are the main questions.
Do we have a final too?
Sorry?
Do we have a final after this exam?
Do you have what?
He's talking about the final.
It's not.
I'm talking about final.
Okay.
Okay. So we have the practice exam for the final online already, right? So today we're gonna do it. So the first question is, right? So this is the practice exam for the final. Final practice exam.
So we don't have class next week, we just have...
We have class next week, right? So we have on Friday, on Monday, right? So the last class is on Monday. So on Monday we're gonna do wave, right? So the wave will not be in the main questions, it's gonna be in the optional questions. Final practice exam, you have UT is UXX. 0 is smaller than x, smaller than 2. T is greater than 0. So heat equation. So you have u of 0t. So this is x is equal to 0. This is 0. When x is equal to 2, you have what? You have u2t will be 0. And when t is 0, u of x0 is 2 sinus of pi x over 2 minus sinus of n pi, pi x, sorry, pi x plus 4 sinus of 2 pi x. And this is the initial condition, right? Right, so this is a similar problem with the previous one, except that you have a different boundary condition. So it's exactly the same problem, except that you have a different boundary condition, right? So you have 4 ut is equal to uxx. So first derivative in t, and here you have second derivative in x. So this is the heat equation, because you have first order differential equation and second order differential equation. So this is heat equation, right? Now the x is considered from 0 to 2. You need two boundary conditions because you have a second derivative in x, right? So you have u of 0t 0, u of 2t 0. So this is boundary condition, right? Boundary condition. And this is the initial condition. All right? Now we have to solve this problem. So step number 1 is going to be the same, right? You're going to use separable method. You're going to split the equation into an equation of t and an equation of x, right? Right, so again, I explain again. This is a PDE. This is a partial differential equation because you have partial derivatives, right? You have partial derivative in t and partial derivative in x. So what you do is you turn that into an ODs, a differential equation in which you don't have partial derivative. In order to do that, you define u you suppose that UTX has the form TT times VX, right? So I put a detailed solution online. You can follow that one as well. So now I'm gonna plug this back to the equation, right? So you have UT will be T prime of T Vx, and UXX will be T V second of x, right? So now after you suppose that the solution is separable, so the solution is the product of a function of t and a function of x. What you do next is you take the derivative in t. So ut will be t prime vx, uxx will be t v second, right? So for ut is uxx means that you have for t prime t vx is equal to tt v second of x. All right? Now you want to separate the variables, right? So you're gonna put all of the guys that have t onto one side. So you have for t is v second x vx, right? So you divide vx to the other side and you divide t to the other side, right? It's good. I explain again. So after you do separable, you're gonna have for t prime v second. So I'm gonna split the variable, right? So I'm gonna divide t to the left hand side and v to the right hand side. So what I have is for t prime over t is v second over v, right? So this is the function of t. Function of t. And this is a function of x. And a function of t is equal to a function of x, which means that this is a constant. I'm gonna put this to be minus lambda, right? So in the solution I put it to be lambda, but this is the same, right? So now I'm gonna have the first equation for t prime over t is minus 4 minus lambda, which means that for t prime is minus lambda t, or you have 4t prime plus lambda over 4t is 0. All right, and the second equation, v second of v is minus lambda, which means that v second is minus lambda v, and this means that v second plus lambda v is 0. All right, so I explain again. After you suppose that the solution is a product of a function of t and a function of x, right? So you plug everything into the equation, you find that for t prime v is equal to t v second. You divide t to the left hand side and you divide v to the right hand side. You have that this is a function of t and this is a function of x. So two functions of two different variables are equal only when they are constant, right? So which means that this is a constant. Right, so now I look at the first ratio. So I have for t prime over t is minus lambda. So I wrote it right here, which means that I have for t prime is minus lambda t, and this is equivalent with t prime plus 4 lambda over 4 is t is 0. The second one is v second over v is minus lambda. So then I get v second plus lambda v is 0, right? Now I need to find the boundary condition for v. Boundary condition for v. Boundary condition for v. So I have u 0t is 0, which means that v at 0 times tt is 0. So which means that v at 0 is 0. Right? And u of 2t which means that v at 2 t of t is 0, which means that v of 2 is 0. Alright? It's clear? So I'm gonna put this guy and these two guys together and I solve the second equation. V second plus lambda x plus lambda bx is 0. X is from 0 to t, 2, and v0 is equal to v2, and this is 0. Right? So I explain again. After I do the splitting, right? So after I do the separable method, I suppose that u is t times v. I plug into the equation, I obtain two equations. The first one is this circle, which is an equation for t. And the second one is this square, which is an equation for v. Alright? So I want to solve the equation for v, but I need the boundary condition. Alright? So I'm going to use these two boundary conditions, u at 0 and u at 2. So u at 0 is 0, which means that v 0 times t0 is 0, which means that v at 0 is 0. So what happens if t is 0? What happens if this guy tt is 0?
It just be a trivial solution.
Yes. So if this tt is 0, you plug it here and u is 0. Right? And u is 0 is not a solution of this equation because you have this initial condition. Right? Can you sign at the back of the paper, please? Alright? So I found v of 0 is 0 and v of 2 is also 0. So I have a eigenvalue problem to solve. And this is a standard problem. So I'm going to have to solve it. To solve this eigenvalue problem, what should we do? Characteristic equation. Can you sign at the back of the paper, please, both of you? So, characteristic equation. Alright, so you have x squared plus lambda is 0. So case number 1, lambda is negative, right? Case number 1, lambda is negative, right? So when lambda is negative, you have x squared is minus lambda, and this is the absolute value of lambda, right? So you have two roots. So the first root will be, root number 1 will be square root of lambda, and root number 2 is minus square root of lambda. Alright, so explain again. Now we have to solve the eigenvalue problem, but this is standard. In order to solve this eigenvalue problem, what you do is that you look into the characteristic equation, which is x squared plus lambda is 0. Now what you do is you consider two cases. Case number 1, lambda is negative. Of course, in this case, you don't have any eigenvalue, right? So it's trivial. So to see that, let us go step by step. You have x squared is absolute value of lambda. So the first root will be square root lambda, and the second one is square root minus square root lambda. So then you have two solutions, right? So you have Vx will be C1 exponential of minus square root lambda x plus C2 exponential of square root lambda x. Alright, so this is what you have. Now you're gonna use what? Boundary condition. Can you sign at the back of the paper, please? So you're gonna use the boundary condition, right? So you're gonna use V0 is 0. So when V0 is 0, this means that 0 is C1 exponential of minus square root of lambda times 0 plus C2 exponential of square root of lambda times 0. So this is 1 and this is also 1. So this gives you C1 plus C2 is 0. Right? So when C1 plus C2 is 0, C2 is minus C1. So the Vux will become C1 exponential minus square root of lambda x minus C1 exponential of minus square root of lambda x. Right? This equation is very standard. So I explain again. So you have an eigenvalue problem. The first step is to consider the characteristic equation. So after you have the characteristic equation, you consider three cases. One of the cases will give you the eigenvalues and the eigenfunction, and the other two will give you trivial solution. So in this case, I have lambda is negative, so I have two roots. They are all reals. So in general, when the two roots are all reals, you don't have eigenvalues and eigenfunctions, right? So to see that, I suppose that V is C1 exponential minus square root of lambda x and C2 exponential of square root of lambda x, right? So I'm gonna use the boundary condition at 0. So V0 is 0, which means that 0 is C1 plus C2 because I replace 0 here. So I found C2 is minus C1. So then I modify the form of, yes?
Well, we've done problems in the past where more than one case has given us eigenvalues.
Yes.
So what happens if that?
So that case, in that case, that corresponds to case number 2, right? Case number 2 is when the b squared minus 4ac is 0. In that case, you can find an eigenvalues and an eigenfunction, but normally the eigenfunction is 1.
And then we can ignore it?
No, you can. You have to add it to the basis, right?
Okay.
So it's going to be 1 cosinus something.
But we'll never have both sine and cosine?
You have 1 cosinus sinus. This is the case of the Fourier series, right? So in the case of the Fourier series, so how do you find a Fourier series? So you have what? You have v second plus lambda v is 0. You have, I think, u at L is u at minus L, and u prime at L is u prime at minus L, right? So this is the eigenvalue problem. So in this case, the second case will give you 1, 0 and 1, right? And the last case will give you cosinus and sinus. So the basis finally will be 1 cosinus of n pi x over L and sinus of n pi x over L. Right? This is the Fourier series. Alright? So in the last case, you're gonna find cosinus and sinus, and at the same time, in the second case, you find 1. So you have to add 1 to everything. And then you have a basis for the Fourier series. Right? So the Fourier series is just one special case of the eigenvalue problems. Right? Alright, so now let us look at the second boundary condition. You have V2 is 0. So this gives you V2 is 0 is V2, and this is C1 exponential of minus square root lambda times 2 minus C1 exponential of square root lambda times 2. Right? So this is C1 into power minus square root lambda times 2 minus e to the square root lambda times 2. So 0 is C1 times a constant, so C1 is 0. So C2 is also 0, and you have trivial solution, right? So I explain again. After the first boundary condition, after you replace the first boundary condition into the equation, you found that V is C1 exponential of minus square root lambda x minus C2 exponential of square root of lambda x, right? Now you're gonna replace 2. You're gonna use the second boundary condition. When you use the second boundary condition, you're gonna find 0 is V2. You replace 2 here. So here you have C1 and a constant. So C1 is 0. C2 is also 0. So in this case, there is no eigenvalue and no eigenfunction. All right? Questions? This is very possible. Now, case number 2. Case number 2, when lambda is 0. when lambda is 0, you have v second is 0, which means that vx will be ax plus b. Right? When lambda is 0, you replace it here, you have v second is 0, which means that v has to be ax plus b. Now you're going to use the first boundary condition. b0 is 0, which means that a times 0 plus b is 0, which means that b is 0. So now I modify vx to be ax. Alright? So I explain again. So in the second case, it's always the easiest case. When lambda is 0, v second is 0, so vx should be ax plus b. Now, you use the first boundary condition, b0 is 0, so then you have a times 0 plus b0, so b is 0. So vx should be ax. So now v2 is 0, meaning that 2a is 0, so a is also 0, so b is 0. Alright? In the first case, using the first boundary condition, you found that b is 0. Using the second boundary condition, you also find that a is 0. So in general, you have a trivial solution. Right? Questions? Skip. Now case number 3. Lambda is greater than 0. Right? So then you have two roots, right? I square root of lambda, and second root is minus I square root of lambda. Right? So then you have vx will be c1 cosinus of square root of lambda x plus c2 sinus of square root of lambda x. Right? So in general, the last case is the most important case because you have sinus and cosinus, and that gives you the basis. The last case is when lambda is positive. When lambda is positive, you find two roots. The first is I square root of lambda. The second is minus I square root of lambda. Right? Then you solve this and you find Vx is C1 cosinus square root of lambda plus C2 sinus of square root of lambda. Alright? So now we're going to use the boundary condition. You have B0 is 0, which means that 0 is C1 cosinus of square root of lambda times 0 plus C2 sinus of square root of lambda times 0. Alright? So after you found this formula, you're going to use the boundary condition, right? At 0, it is 0. So you have 0 is C1 cosinus of square root of lambda plus C2 sinus of square root of lambda times 0. So this guy is 1 and this guy is 0. So you have 0 is C1 times 1 plus C2 times 0, and this is C1. So C1 is 0. Alright? So the first boundary condition is 0, which means that you have 0 is C1 cosinus of 0 plus C2 sinus of 0. So the second one is 0. Then you're going to have 0 is C1 times 1 plus C2 times 0. And this is C1 because C2 goes away. In other words, you have C1 is 0. So now I'm going to modify B to be C2 sinus of square root of lambda. Right? Because C1 goes away. C1 is 0. Right? Now I'm going to use the second boundary condition. Right? B2 is 0, which means that 0 is C2 sinus of 2 square root of lambda. Right? C2 is, V2 is 0, which means that 0 is C2 sinus of 2 square root of lambda. So 2 square root of lambda will be n pi. So lambda n will be n pi over 2 square, and then you're going to have Vn is sinus of n pi over 2x. Right? This is what you obtain after solving step 2. So after solving step 2, you have that lambda n is this guy and Vn is this guy. You don't have to take a picture. I have the solution online. Right? All of this is on the solution that I put online. Right? So it's very detailed. Right? So lambda n is n pi over 2 square, and Vn is sinus of n pi over 2x. Right? So step 2 is quite standard. Right? Alright, except that in the solution online I put minus lambda, so I have a minus. But this is the same, right? Question? It's good. So at the end of step 2, so step 2 conclusion. So for this equation, V0 is V2 is 0. All right. So you have Vn of x. We have is sinus of n pi x over 2, and lambda n will be n pi over 2 squared. Right? So at the end of step 2, the conclusion is that lambda n will be n pi over 2 square, and the eigenfunctions will be sinus of n pi over 2. Right? Questions? Now step number 3. We're gonna solve the other problem, right? So this is solve the equation for x. Right, so step number 2 is to solve the equation for x. Now you have to solve the equation for t, right? Solve the equation for t. Right, so you have Tn, t plus lambda, t prime plus lambda t is 0. This is the equation for t, right? So now I'm going to plug this guy into the equation. I have t prime plus n pi over 2 square t is 0. Yes?
I thought the equation for t was t prime plus lambda over 4t for this problem.
Thank you. Yes, very good. Can you say at the back of the paper, please? Yes, that's 1 over 4. So the equation for t is t prime plus lambda over 4t is 0, right? So which means that you have t prime plus 1 over 4 n pi square over 2t is 0, right? So how do you solve this equation? This is first order differential equation. You can solve by separable, or you can integrate it right away. So you have t prime is minus 1 over 4 n pi square over 4 of t. Right? So this is minus n pi square over 16 of t. Right? So to solve this equation, you put everything to the right side. So it's going to give you minus 1 over 4 n pi square over 4 t, and this is n pi square over 16t, right? Now this is again separable, right? So you have t prime over t is minus n pi over 16 squared, right? This is again separable. Why? Because this is t and this is t. So what I do is that I divide t to one side, and the leftover is something else, right? So the t is on the left hand side, and the other term is on the right hand side. So this is still separable. All right. So what is t prime over t? Yes, log of t. Can you say it back up the paper, please? So this is log of t. prime, and this is minus n pi over 16 squared, right? And so you integrate that. So you integrate that, and you have log of t will be minus n pi over 16 square into a, and this is minus n pi over 16 square plus a constant, right? It's good? It's clear? So, again, this is separable because you have t prime and t. But what you do is you divide by t. So on the left hand side you have only t, and on the right hand side you have only the constant. So this is separable again. So separable means that you divide to both sides so that on one side you have one guy and on the other side you have the other guy, right? So t prime over t will be log of t prime, and this gives you minus n pi square over 16. This is it, yes?
So what does it have a t on the right?
Excellent, thank you. Can you sign at the back of the paper, please? Right, so now you're going to integrate. So log t will be the antiderivative of n pi square over 16, and so this is minus n pi square over 16t plus a constant t, right? So to find t, I just have to integrate. So this gives me exponential of minus n pi square over 16t plus c. I call this c0, so this gives me e to power minus n pi square over 16 e to the c0. I call this to be c. And this is c e to power minus n pi over 16t. Alright? This is quite easy to solve. Right. So again, this is the basis for the x. Right? So you have to multiply with this guy. You ignore the constant to have a basis for c, for t and x. Right? So I explain again. You have t prime is t times something, right? So this is separable because you can divide t to the left hand side so that t is on one side and the other side is something else. So t prime over t is log t prime. So log t prime is minus this constant, so I just have to integrate and have log of t is minus n pi square over 16t plus a constant c0. Now to find t, you just have to take the exponential of both sides. I'm gonna have exponential of minus n pi square over 16t times exponential of c0. So exponential of c0 can be a constant c, right? Because it's arbitrary. So finally, you have the basis, which is the product of the two guys, right? Step number 4. The basis will be exponential of minus n pi square over 16t times sinus of n pi x over 2, right? So in step number 4, the basis will be the product of the exponential and these eigenfunctions. So in the next step, we're going to have to find the constant for this basis. All right? So this, we're going to continue this on Wednesday. It's okay.